Hello everyone, my name is Teja and welcome to this probability refresher for business analytics and machine learning video series. Today we're gonna look at counting as a tool to estimate probabilities. So as a tool to compute probabilities. So let's warm up with some. Let's remember these topics that we might have seen before. Um, so I'm going to look at permutation, combination, and the notion of power set. So, okay. So, so how do we count? So let's start with our first example. Let's say I have, um, let's say, three stages. Okay. In each stage, I can do 5 actions each. For example, I'm playing a video game, and maybe I'm in stage one, as in I'm presented in the first screen. I can do 1 out of 5 actions, and then given that action, I go into the next stage, and in that screen, I again have 5 options, maybe, and I can take one of the actions, and again I go to the third screen, and I get to take one of the 5 actions. Then the question is um, how many paths, or how many total possibilities are there in terms of sequences of actions that I can choose. And this can be counted easily. So I have 5 actions each. So 5 actions I can take in the first stage times 5 actions I can take in the second stage. So by the end of second stage, I could have taken possibly 25 different sequences of actions times 5 again, which is the number of actions possible in third stage. So by the third stage, I can take 125 different action sequences. So for example, in the first stage, um, I could have taken action 1. In the next stage, I could have again taken action 1. At third stage, I could have again taken the action 1, right? So that's one sequence of actions. But at the same time, I could have taken action 1 and maybe action 2 and again maybe action 2. And you can see how this is going. I could have taken action 1, action 2, and maybe action 3. And so if you count all the number of action sequences, it's 125. So you multiply the number of choices that you have in each stage. Okay. So that's first example. Second one is the number of ways to order, let's say, n items. Okay. So I have a banana, an apple, and an orange. Okay. So I've just used letters BAO. So banana, apple, and orange. So how many number of ways can I order these 3 items? Okay. So first, one order I have already written. So I can keep the banana in the front. Then I can take orange, and then I can take apple. Or uh, I can do apple first, banana, and orange. I can do apple first again, orange, banana. Or I can do orange first, banana, and then apple. I can do orange first, apple, and then banana. You can see that I can't really do any other way to order these 3 fruits. So this is 6 ways, and this is called a permutation of n elements, in this case 3 elements. And the notation for this is 3 factorial. So factorial, so think of this as like a factorial of 3. Okay. So it's like saying it's a function which acts on 3. 3 is the number of elements. Given 3 elements, I'll tell you how many number of ways you can order them, and that's this function. And shorthand way to represent that is to write 3 exclamation mark, and that's equal to 6. And there's actually a nice formula for this. So this function with this argument 3 is equal to 3 times the previous number 2 times the previous number 1 till you get to 1. Okay, so in this case, it's 3 times 2 times 1. Okay, so that's the permutation. So let me talk about a third variant, which is the combination. So this is the number. I'm using the hash symbol to use as a shortcut for numbers. So number of ways to select, let's say, k items out of n items. Okay, so maybe my n items are 5, and I want to select 3 items. Okay, so how many number of ways can I select 3 items out of 5 items? Okay, so this one we can do as follows. Let me do an example. So let's say there are 5 items here. So A, B, C, D, and E. So number of ways can I can select 3 items. So I can select A, B, and C, right? I can do this. I can do A, B, and D. I can do this. These are three items. I can do A, B, and E, right? So this is the this is one um, some um, 3 items in this case, and note that there is no order information here. I just need to select 3 items. There is no special meaning behind A first, B second, and C third. So what else can I do? I can do B, C, and D. I can do B, B, A, and D, right? B, A, and D. I can do B, A, and E. I can do B, C, and E. So just ensure that I'm not repeating something. So B, A, and D, and A, B, and D is the same. Okay, so clearly I'm not good at this. I'm just trying to do it online. So that's the 3 additional sequences. So B, C, and D. Okay, it's not done. A, B, and E has also been done, so I need to cut that out. And B, C, and E has not been done. So is this exhaustive? Actually, okay. C, B, and E has not been done. So that's one more sequence. So I think this is it. So if I choose anything else, it may turn out to be one of the previous ones. So let's see. It's actually a closed form, as in a simple formula again. The formula is n factorial divided by k factorial times n minus k factorial. So let's actually put it into the, let's use numbers. So 5 factorial divided by 3 factorial times 5 minus 3, which is 2 factorial. This is equal to 5 factorial and 3 factorial cancel out a bunch of these product terms that I showed in the previous page. So I have 5 times 4, and 2 factorial is just 2 times 1. So this is equal to actually 10. I only wrote 6. So okay, I need to figure a few more out. So okay, B. So what all was involving E? So BC. So what about B, D, and E? Okay, B, D, and E. So we got 7. What about A, D, and E? A, D, and E was not done. And then BC, BD, BE, ADE, ACE. What about ACE? ACE was also not done. And ACD. Okay, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I think this is it. Unless I'm okay. I think this is the very exhaustive way of doing it, even for such a small example. But you can check that this is actually the way to count it. I just gave you the formula, but so this is the combination. And let's see. Another counting example is the power set. Okay. So what is the power set? It's the set of all subsets of a given set. So if a set, let's say I have a set omega, which is 1, 2, and 3, then power set, which is a symbol to use is 2 to the power omega, it's just a symbol. Just think of it as set. Let's say set C. Then set C is going to be the empty set, and the set 1, the set 2, the set 3. Okay, these are all subsets of the sample space, and we can use 1 and 2, we can use 2 and 3, and we can use 1 and 3, and we can use omega itself, right? So how many sets are there? 1, 2, 3, 4, 5, 6, 7, and 8. So this is the collection, this is the power set, and the size of the power set. So size of a set is represented using these vertical lines. So size of the power set is 2 to the power the number of elements in the original set, which is 3 here. So size of the power set here is 8. Okay. So in general, if there are 10 elements, the size of the power set is 2 to the power 10 if I include the empty set. If I don't include the empty set, you have to do 2 to the power n minus 1. Okay. So that's the power set. So what is a simple application of this? So there is this, so we saw the number of times we can have, so let's compute the number of times we can have k heads in n trials. Okay, so this is like I repeat flipping the coin n times, and I have observed k heads. The question is, what is the probability, what is the belief about this, assuming that each trial is independent? This is the same as out of n trials, k locations I have heads. So I don't care about which locations I have head in the net. After n trials, I have k heads. And since I have k heads, in those trials, I would have had those heads appear with probability p to the power k, in the sense there are k locations where there are heads, and at each location, the probability that a head would have happened is p to the power p. So it's p to the power k. And the remaining locations, which are n minus k in number, I should have a tail. Otherwise, I would not have k heads, right? Otherwise, I would have k plus 1 or k plus 2 heads. So this is going to be n minus k. So this is the probability of k heads in n trials, and this is going to be an integral element in defining what is a random variable, and in this particular case, binomial random variable. So this is it for this video. Thank you for watching.